Okay, great. Sorry, I don't know if
Yes.
you're like killing time for me or not. I was just just checking there. So, and I don't know if is the screen showing? I'm still seeing a different screen on your room.
Yeah, not yet. Keep
Okay.
trying.
Well, so I think everybody online can see my screen. You guys are not looking. Yeah, I'm getting thumbs up from the people online. I don't see my screen displayed on your projector though.
All right, give us a second.
Okay.
There we go.
Hey.
Hey, all right, cool. Okay, so you're seeing Mars and like old Mars, wet Mars, red Mars, blue Mars, red Mars kind of stuff. Is that right?
Yep.
Okay, great. Okay, cool. So thanks for having me again. Thanks for the good intro there. It's always fun to chat with you guys and see all the cool stuff you're doing. So yeah, as Kevin said, I'm going to be talking to you guys about Mars. This is actually an area I spent about 14, 15 years of my life working on, helping design and operate rovers on Mars. So kind of like last time, it's a little bit of a whirlwind thing, right? I've got a bunch of content. I'm going to go pretty quickly, so fasten your seatbelts. And to try to keep a reasonable scope here, right? I'm really focused on the surface missions. That's what I worked on. That's what I know the most of is, kind of the boots on the ground missions. Though I will hit a little bit on some of the other stuff, some of the flyby stuff, but the general focus is going to be on rovers and stuff. So we're going to hit a little bit of Mars background, early ground-based observations given the audience, right? That's what you guys do. And then early space age, Viking, back to Mars in the 90s, and then modern era, and some thoughts on future exploration. So, and ask questions anytime, and I think I have an hour, so I'm going to go quick. But I'm happy to hang out later if you guys have questions or whatever. Um, I mean, of course, this is, you guys should know this, right? Mars is rock number 4. Kind of maybe more generic, not something you guys need. Maybe you haven't thought about this in a while. This is just a little bit of a scale comparison. So this is a picture of Earth on the left with our tilt, right? 23.4 degrees, 24-hour day. Mars on the right, about 1/3 the gravity of Earth, about half the diameter, a little bit less than half the diameter. And surprisingly, the tilt is the same and the day is roughly the same. And it turns out if you're driving rovers on Mars, that matters a little bit. I can talk about that a little bit later. But if you're doing Mars time operations, which we do, basically you show up Monday at 8 o'clock for work, and then you show up Tuesday at 8:40, and over a 37-day period, you kind of walk through first shift, second shift, third shift stuff. And when we operate rovers on Mars, we do that for usually like 3 months just to get kind of our bearings and maximize use of the vehicle before we transition to a little bit more of a sane schedule. So fun stuff there. And then the atmosphere of Mars is about 1/100th the thickness of Earth's atmosphere, so substantially thinner, but enough of an atmosphere that you can't just design like a lunar lander, right? It can't be pure propulsive. You need something to deal with the heat of entry, right? Getting through that atmosphere. When you get to Mars, you're usually going 5 to 6 kilometers a second. So you got to get rid of all that energy without burning up. And then down below, it just talks about the composition a little bit, right? Our atmosphere is mostly nitrogen with oxygen. Mars is like 95% CO2 with a little bit of nitrogen, 3% nitrogen, and then trace gases after that, basically. So anyway, a little bit of orientation there. So diving right into observations, right? Kind of going back to ancient times. So the Egyptian astronomers were the first to really record Mars as a wandering object in the sky, that we saw in the written record, as kind of having a weird path, right? You see this picture on the left that kind of shows the back and forth, right, depending on the relative position of Mars and Earth as they're moving around the sun. So, and there's just a lot of the planets. Mars was found on the ceiling of the tomb of one of the pharaohs in Egypt, right? Shown up in star maps, ancient times. Um, Including a star map that was dated all the way back to 1534 BCE, right? So people have been looking at Mars for a long time, but for the vast majority of human history, right, it was a dot in the sky. And that changed, of course, with the telescope showing up in the, 1500s, I think, with Galileo and others. It turns out the first recorded like feature, so not observation, but like surface feature, Christian Huygens had a powerful enough telescope that he was able to kind of sketch out a feature that he thought he saw on on Mars. And one, I guess this is kind of funny, like the eyepiece, you can see the north is down, south is up. So he's reflecting the, the fact that the eyepiece inverted that picture. And that feature we think was probably Syrtis Major, which you'll see in some later pictures as well. Anyway, so that was kind of a milestone, 1659, first beginnings of it's more than just a dot of light in the sky. Then, of course, one of the more controversial elements, right, as our telescopes got better and better over time, we started seeing things, but what were we seeing really, right? So Giovanni Schiaparelli started mapping Mars with a 22 centimeter or 8.7 inch telescope in the late 1880s, and he thought he was seeing canals. So he did this over, more than the order of a decade of time. He put together this map, which was kind of implying maybe not just natural features, right? Late 1800s. But even in the 1800s, right, if you kind of do some homework, turns out there were detractors of the canal theory. So not everybody subscribed to this being signs of Martian civilization. And then, of course, in the US, right, the famous person, Percival Lowell, founded his observatory, and he had kind of the next size up 30, 40, and 45 centimeter telescopes that he dedicated a substantial amount of time to making right, Mars observations with. And he thought he confirmed the canals. And not just him, there was another astronomer in Nice, at the Nice Observatory, southern France, right, on the high hilltops down there, that also, and I don't know if this was groupthink or not, but like those guys thought they were seeing canals. But starting in 1909, Eugene Antoine Antionati, even though he was in the late 1800s, he was kind of a proponent of the canals. When he started looking at the data more, he thought, he convinced himself he didn't think they were real, and that was, of course, with a much bigger telescope, an 83 centimeter telescope in France. I think it's France. Anyway, so even though there were detractors, and it kind of by the early 1900s, the canal theory had kind of been debunked in most circles, there were still theories of Mars, alien civilizations on Mars, like basically all the way until we got Mariner 4 to Mars in 1965, right? So there's this question like, right, are there Martians on Mars or not? And then 1964, this is an example of one of the Mariner 4, right? A US flyby probe took a picture and kind of like put the kibosh on all of that stuff, all of the speculation that happened before. One of the fun things that Kevin wanted to make sure I pointed out, so the source here was Kevin. So in the late 1877, the telescope at Foggy Bottom, right, the Naval Observatory, Asaph Hall, discovered discovered Deimos on 12th of August, and then Phobos on 18th of August, right? These are these kind of tidy potato moons of Mars that were not discovered very early, took a while to get discovered because they're just not very large. And I guess your guys's one of the telescopes you're affiliated with, the UVA McCormick Observatory, actually helped confirm the detection of those moons. So kudos to you guys. Okay, any questions on that stuff? Otherwise, I'm going to move on to kind of space age, which is more my thing.
Questions? No? Okay.
Was that a no?
Dan.
Yeah,
We'll
keep going.
just
Okay.
keep going.
So this is a cool graphic that the Planetary Society put together, or no, was it I guess Harold Clinette, sorry, 2013. So, and Brian Christie, that put this together. So I kind of use this graphic in a bunch of places where like an infographic that's kind of showing at least up and through 2011, all the missions that had gone to Mars. The colors are kind of flagging the country, not whether pass fail, right? So red is either Soviet Union for the most part. I guess later on there's some Chinese ones, and then U.S., Russia, etc. And it turns out up through 2011, 47 missions launched, 2/3 failed. Right, so there was kind of this the big kind of the Mars, I guess, gremlin or ghoul or whatever. A lot of the missions that failed, even though the vast majority of the U.S. missions did succeed. The Russians were just not very successful at Mars. They were doing great at Venus, but most of their Mars stuff failed, and even that continues to modern times. Most like all of their Mars stuff has pretty much failed. So anyway, so early space age. Really, I'm just going to focus on Mariner 4 for the most part. But we had, I guess the Soviets had a few partial successes. They made it into orbit. They failed their landing, or they might have landed and then had like one picture sent back in the case of Mars 3. But for the US, our first successful flyby mission was actually Mariner 4, right? But anyway, going to focus on Mariner 4 a little bit. So this is kind of one of the cool little pieces of Mars history. So back in the day before high-speed, radios in space and giant antennas, or even with giant antennas, right, the telecom capabilities were just not great. And so when we were getting the bits back from Mariner 4 at JPL in 1964, whenever it was, the team did not have the patience to wait for the computer to generate the image. So they basically read out the numbers and they just started hand coloring to the binary. So this is like a hand-drawn picture, the engineer's interpretation of what the numbers, like it's almost like watching the Matrix, right? Like watching the numbers across the screen, and then they were kind of hand coloring the interpretation coming in. So that I thought that was really cool. This picture is actually, the original is like hanging at JPL, kind of an old, space age artifact. One other fun thing, so when they were planning and like documenting, both planning the Mariner 4 flybys, and then even when they were documenting like where they took the pictures, this background map, this globe map, I thought was just kind of funny to look at. It's kind of the quality of the map that Lowell put together, right? Late 1800s. Like we didn't really have much better than that all the way up to 1960. So that was really the main point of this image. And that's what you see. These little rectangles are just the projections of where the Mariner 4 images were taken. And then this is just a little, how well did our engineers do hand drawing the map versus when the image finally got processed. They're a little different. You definitely would interpret these a little differently, but anyway, kind of close, right? So that was Mariner 4. And then, we had a few other flybys. We had Mariner 4, 6, 7 were flybys. 8 failed. Mariner 9 was actually an orbiter, and it actually did halfway decent, imaging of the whole planet. I'm not going to go into all those details, right? We just don't have time. But then after that initial set of recon, we went, the US kind of went all in on what I would call like this glorious Hail Mary on the Viking mission, which in roughly today's dollars, I think it's like probably a $5 billion mission, sending 2 orbiters and 2 landers to Mars, and they both worked. This was JPL working with Lockheed Martin. Lockheed built the landers. We built the orbiters and we launched everything. We were the overall program managers. And this shows on a map of Mars. I think this is a Viking, sorry, not Viking, like a Mariner 9 quality map of Mars where Viking 1 landed and where Viking 2 landed. Some pictures, right? These are like humanity's first pictures of Mars in the 70s. So very rocky. We kind of got lucky we didn't die, right, on this landing, because like super rocky landing field in the case of, I think, Viking 1. And then Viking 2 was a little further north and actually had some seasonal snow cover. I think this is CO2 frost. So on Mars, it gets cold enough that the atmosphere literally just freezes out. There's no like wet precipitation. It just goes from gas to solid when it's cold enough. And the atmospheric pressure actually drops by like factor of 2 during the winter, the coldest winter season, which I think is Southern Hemisphere winter, I think. I forget the exact time. And this kind of shows that pressure. So this is the surface pressure on Mars versus season. So L sub S is kind of like solar longitude. So 0 to 360 is like 1 Mars year, basically. And so you can see this huge pressure wave, not quite a factor of 2, but a substantial pressure variation over the course of the year, right? That's kind of a weirdness of Mars. And by the way, when you're landing on Mars and you have a parachute, this matters a lot, right? Like there's less air. If you're landing L sub S, like 160 or whatever, you've got a lot less air to slow you down than if you're landing in these other seasons. And so there's a lot of things that make different, like landing on Mars hard, depending on the time of year and stuff like that. So anyway, more pictures. One of the things that Viking did was survive a big dust storm, right? Viking was nuclear powered with radioisotope thermal generators. And so even though the deck was like massively dust covered here after several years, and you can see the sky kind of was like blotted out. One of the big controversial items, right? Viking went kind of all in on life detection. That was the Hail Mary element that I was kind of alluding to. And they had 4 biology experiments, 3 of which were clearly negative. one of them was like what do you call it? Metabolism experiment. Like basically take some Mars soil, feed it water with nutrients in it, and see what happens. And because that one looked like maybe it had a little bit of a response. That the PI for that mission was saying he thought he found life on Mars, and he accused people of covering it up. But really, I think after the fact, it turns out there's some active compounds in Mars's soil, and we kind of confirmed this with later landers I'll tell you guys about, that the perchlorate in the soil is probably what was causing this reaction. And then the other thing is, the first injection had some response, and the subsequent ones didn't really have any substantial response. So anyway, that was controversial, took a while to resolve. And then because of that failure, right? We took this. We were looking for the Martians, right? The live things in the soil, and didn't find anything. The U.S. basically started doing other stuff planetary-wise. So like after 1977, when we landed, we did not go back. I think the last lander died like in 81 or something like that, early 80s. We did not go back until the 90s. We tried to go back in 1992. That mission actually failed. That was Mars Observer here. And then the failure of Mars Observer kicked off this faster, better, cheaper period where we just try to go like every couple of years, go to Mars. And so Mars Global Surveyor, Pathfinder, all these missions were kind of spawned from that. And I kind of just hit these points already. So we ended up doing Mars Pathfinder and Mars Global Surveyor in the mid 90s for about $250 million a pop for the flight systems. We landed the first rover on Mars then. This just kind of shows the Pathfinder landing site. And you see a lot of this kind of us, it's like planning your hike, right? Us taking pictures of features on the Mars terrain and trying to triangulate our location on Mars because we don't have GPS and stuff, right? So this is kind of old school navigation, map and compass that we do. I mean, now it's less so, but especially early landings, that's what we did a lot when we were on Mars. And one of the fun things, so you guys might all remember the face on Mars controversy, right? So when Viking was orbiting Mars, it took this relatively fuzzy picture, and due to the lighting conditions, it looked like a mask. And all the tinfoil hat folks were like, "Oh, NASA's covering up this mask," right? So when Mars Global Surveyor landed on Mars, and by the way, this is a giant feature. It's like pyramid size or bigger, right? Like Butte's. It's a small like hill assembly, basically. When Mars Global Surveyor showed up with its like meter resolution class imager, it kind of confirmed like it's just a giant rock, giant hill, and that's not any kind of sign of civilization. So anyway, that was kind of a fun thing from those two missions. And then because we did it for $250 million and we were in this faster, better, cheaper era, NASA asked us to do the next missions for $125 million a pop. And the bottom line is they both died. So we had a lander and an orbiter. Mars Climate Orbiter basically had an error because of some units, but the bottom line is like the team was overworked. They couldn't cover all the open issues. This thing slipped by. They didn't take into account a force issue because of some unit error, conversion error. And instead of flying by, at a good altitude, they kind of came in too low and burned up the atmosphere. So we lost that mission. And then the lander, Mars Polar Lander, had an error where they weren't, because of budget, weren't able to test the lander end to end, like this whole landing sequence. We think when the landing legs deployed, the springs, like the springiness of that action triggered the landing detection. Like the thing thought it was on the surface, and it cut off the engines and then fell like the last kilometer to the ground, or sorry, last 40 meters to the ground, and crashed and died. So that was a bummer. So I think we kind of learned there that you can do faster, better, cheaper over decade time periods, but in short periods, you kind of get to pick two of those and not all three, right? And because we're the U.S. government, it kind of doesn't look great when we fail. People accuse us of wasting taxpayer dollars and all that stuff. So after that, we became like way more conservative again in our missions. Okay, so then after the 90s, we kind of transitioned from faster, better, cheaper to a little bit more conservative, right? Engineering and budget-wise. And we also matured the strategy to this kind of follow the water, and I call it follow the water plus. Now we're doing habitability. And that strategy really kicked in starting in the early 2000s. what I would call the modern era Mars exploration. So this is kind of a different view now. We're kind of zooming in, right? This is the last of that big picture view. We're zooming in now, early 2000s all the way to 2020. What was going on, right? So up above are all the orbiters that are active, and actually, so all of, just FYI, like all of these missions that got to Mars in the early 2000s and beyond, all the orbiters are still flying. They're all working great, including Mars Odyssey. I mean, it might be dying, like Mars Odyssey is kind of on its last legs. Everything else is still working pretty well. Um, and I'm going to jump into now kind of focusing on the bottom for the most part of these things. I guess before I move into the surface missions, this is the kind of stuff. This page is just the collage of the fun things we can see from orbit, right? So we map the entire planet. We have huge swaths of the planet now mapped at kind of half-meter resolution. So Mars Reconnaissance Orbiter has the kind of a SpySat class, telescope on it, like, almost SpySat. And we've seen all these cool things, including like an avalanche in progress, right? Was a picture that we kind of got lucky taking at one of the poles of Mars here. You can see, this kind of time lapse in the lower left of seeing kind of some kind of water feature, we think, changing the color lineations and stuff like that seasonally on Mars. We've also seen, again, dust storms were, clear seasons versus in June of 2001 versus September, Mars had a huge global dust storm. So you can kind of see what that looks like from orbit. We have now, because of a laser, the rainbow color map is from a laser altimeter, where we have very high resolution topography of the planet. And because Mars has no ocean, right, we actually know the topography of Mars globally better than we do of Earth, because 3/4 of the Earth is underwater, right? And it's very hard to make high resolution, uh, topography measurements in the ocean. We don't have high resolution sonar everywhere, basically. Anyway, so cool stuff that we've seen from orbit. But really now we're going to jump into all the fun little surface missions. So I worked on Spirit and Opportunity, and I worked on Curiosity before I transitioned to doing Earth science stuff. So talk about those a little bit. So one of the highlights, there's each of these missions have, like, I could spend an hour talking about each of these missions. This is one of my favorite scenes from the Spirit and Opportunity rovers. This is Spirit on Husband Hill looking across Gusev crater and seeing this dust devil parade come through, right? So Mars definitely has dust devils. There's enough atmosphere for that. And it turns out like these rovers lasted a lot longer, because these wind events, like we actually saw a dust devil come over our rover and like clean the solar panels off, right? These were solar powered missions. We thought they'd only last 3 months. They ended up lasting 6 years and 14 years roughly, respectively. And partly due to the nice windy days that we got that kind of washed the car. One little fun blast from the past. So you see me kind of with white hair here. This is a cool picture a friend of mine just sent me recently. This is Steve Squires, the kind of very charismatic and fun to work with PI for these missions. On landing day, this is Justin Mackey, a buddy of mine, and then this is a younger version of me in the control room. And then this is a picture from Opportunity, totally different part of Mars that it was driving around on. But both these missions together, they basically proved water existed on Mars in the past. Right, we had hints, like we were seeing these things from orbit, but scientists being scientists, just relying on morphology from orbit wasn't necessarily 100% proof, right? So we had instruments on these rovers that proved there was water in the past on Mars. At least acidic water is what we really could definitively prove. And a lot of evidence for groundwater activity was kind of their main contribution. Then Phoenix landed, and again, just interrupt me if you guys have any detailed questions. Phoenix landed in 2008. And the reason it was called Phoenix is, if you guys remember that 1998 polar lander that died, this was kind of the rebirth of a lot of that hardware, second chance for a lot of that hardware. And so it landed at high latitude. And even so what you see, just a few fun pictures here, upper left-hand corner, the landing jets, right? You can kind of see these little silver cones. Those are the landing thrusters from Phoenix. And they dug up the dirt, and so the dirt has like ice and soil mixed in it. It kind of like melted all that, and you can see kind of the refrozen water. So this is a picture taken with a robotic arm looking underneath, and this looks like it's refrozen water from what we probably like melted the ice soil mixture. And so that was kind of a fun picture. Here we're using that robotic arm to dig, and we see water, and most importantly, so in the shadowed spot, lower left-hand corner of my mouse, right, it's kind of highlighted here. When we first dug, there's ice exposed, right? And then kind of like what you would expect, at the temperature and pressure that we saw, within a few days that ice evaporated. And so that helped definitively prove, this is water ice. And then this is just a panorama of the super flat landing spot that Phoenix landed on down here. So again, Phoenix proved present day water ice on the surface, right? Definitively. And also found this perchlorate. So Phoenix had a chemicals lab, and we dumped some soil in there, and it saw perchlorate that this very reactive, right? Perchlorate is a component of rocket fuel. It's an oxidizer, and it's very reactive. It actually is also toxic to humans, right? It kind of inhibits thyroid function in humans or mammals, animals in general. And it turns out this was the first hint that we have this very active, kind of reactive soil on Mars. And again, that helped explain the Viking measurements back in the 70s, what we were seeing. Then we move on to Curiosity. So Spirit and Opportunity, like 170 kilo class vehicles. Curiosity is more like a 1 ton, like almost, it was like 900 kilos, 850 kilos roughly, and more the size of a Humvee, right? So much larger vehicle. You can kind of see it in this little action pose. It had 10 instruments, right? Spirit and Opportunity had 3 instruments and a rock abrasion tool. Curiosity had 10 instruments and a big drill, a scoop, a lot more stuff going on. So like massive vehicle. We spent like 10 years on this. I worked on this from 2004 to 2014, turned my hair gray, but it was a lot of fun. So this is one of the fun shots. So we landed, this is a shot from Mars Reconnaissance Orbiter looking at our landing site, the Bradbury landing site. You can see kind of our jets and how they disturb the dirt there. You can see our tracks, our little tire tracks driving around, and we drove over to Yellowknife Bay and drilled our first drill holes on Mars, which was really cool. You can actually see the rover here. This little reflective feature is the rover on Mars as observed from orbit. And then we just did all this cool science, right? So lower right hand, these are the first drill hole on Mars. So I helped lead the team that was responsible for that surface sampling system that did this drilling and stuff like that. So that was awesome to be part of. A lot of fun, like amazingly smart people on that team. This is Curiosity in Yellowknife Bay. You can kind of see these mudstones. And what we proved with both our X-ray diffraction instrument and a kind of analytical chemistry lab was that these rocks on Mars, these actually were mudstones, right? From orbit, they kind of look like mudstones. That was the theory. And then because we had boots on the ground, we could prove these were actually mudstones, and we proved that life, like when the conditions when these mudstones were laid down and kind of that the water was neutral pH as opposed to the acidic rocks we'd been seeing previously with our other rovers and other locations on Mars. And so neutral pH water, that we can easily imagine bacteria that live on Earth today, if they were around 3 billion, 4 billion years ago when there was a lake here making these mudstones, they would have been happy making a living in that environment. So that's kind of what I just said, right? And then we also confirmed, so with the scoop, we also scooped the dirt just like Phoenix did, and we saw that perchlorate again in a much more rigorous way with our better instruments that we had on this mission. One of the other interesting things about Mars, so there's this persistent, what we call kind of the Mars methane mystery, right? And so there were some orbiters that saw actually ground-based telescopes from Earth that had detected hints of methane in the Martian atmosphere. One of the orbiters had also seen maybe hints of methane in the atmosphere. But then there was a mission, the European Trace Gas Orbiter. I'm going to go back to that picture real quick, right? So this guy, the Trace Gas Orbiter, was like designed to go look for trace gases, including methane, right? Because methane's a big deal, right? In case you don't know, it's either kind of burped or farted by life on Earth, right? To be a little crude, or it can be made by abiotic processes like serpentization and stuff like that. And so this mission was supposed to go and figure out if, kind of corroborate these ground-based and other orbiter results. And that trace gas orbiter could not find any evidence of methane. That was a major bummer. But we send Curiosity there, right? And to our surprise, maybe not surprise, so we had a spectrometer also specifically designed to detect methane at very sensitive levels. And we took kind of samples during different parts of the day, different seasons, and noticed, what looked to be a seasonal signature, right? So summer, autumn, northern hemisphere, summer, autumn. It looks like, this methane signal is stronger, and also a diurnal signature. And we think this is what might be happening. I think Curiosity is mostly making this measurement. I think it was like at night. And the trace gas orbiter was really only making measurements at like a totally different time of day. And we think that the methane was like, it wouldn't last that long in the atmosphere. It was just getting destroyed before the trace gas orbiter could measure it. So we think there's something kind of burping methane on Mars periodically, both diurnally and seasonally. And that's still being investigated, right? It's kind of an active research area, but it might be a hint of maybe deep underground life, or it might be a hint of just, other stuff going on geologically down below. We haven't been able to tell the difference. The next mission that landed 2018 was InSight. This was a seismometer, primarily a seismometer mission to kind of look at the interior of the planet. It also had a thermal probe. That thermal probe ended up it was supposed to like kind of bore its way down a few meters in the ground, and it didn't work. It was kind of a high risk, high reward design that didn't work out. But with the seismometer, we could refine the interior models of the interior, right? So on Earth, we've got gobs of seismometers everywhere. Every time there's an earthquake or anything else happens that shakes the ground, we get a lot of insight into the, what we think the interior looks like, right? So this is an Earth model, right, of like our nice layers inside our planet. And over time, this is, so this is an early Earth model, and now modern models, because of our seismometer data, have these very complex models of the interior of the Earth. So we don't have anything like that for Mars yet, but this InSight mission kind of started letting us do that, and letting us refine a model of what the interior of Mars looks like. How complicated is it? And it did prove that Mars has a liquid core. That was kind of a controversial thing. We weren't sure, the scientists weren't sure if there was a liquid outer core or not. Detected a whole bunch, several hundred, more than 400 seismic events, including a couple of like 3.5 magnitude earthquakes, and then also measured the thickness of the thrust more accurately. Pre-landing, we were thinking the crust might be 100 kilometers thick, and it turns out it was only like 25 to 40 kilometers thick on average. So that's what we learned from that mission. Now we're into the 20.
Daniel?
Yes, sir.
Yeah, quick question. Go back to that slide.
Yep.
So you said liquid outer core. What about the center? Is the center also liquid?
Solid.
Solid.
Yeah. So I think there's like a pressure transition, where the pressure is high enough it goes back to being solid, even though it's hotter.
Okay, thanks.
Yep. That's my understanding, at least. I could be wrong, but that's my understanding. I think it's the same thing on Earth. Okay. And then so 2020 things, so things kind of slow down a little bit. 2018, 2020, we showed up with Perseverance. The Chinese actually showed up with their first lander, and then UAE showed up with their first mission. And I guess maybe to highlight, so up until most like the 2015 timeframe, almost every mission at Mars was either U.S. Successful mission was U.S. with maybe a couple of European, right, representatives. The Indians showed up roughly 2015 or 2014, I forget that time frame. And so now UAE, right? So the United Arab Emirates showed up with their first mission in 2020. The Chinese show up with their first mission. So we're gonna talk about those a little bit. So I didn't work on Perseverance, but a bunch of my friends did. This was the first time we had like high definition video of the landing. Again, I could spend 2 hours talking about just this mission. This is an actual shot, right? Not animation. Camera mounted in the descent stage, looking down at the rover. You can see the bridle, the 3-point bridle that we're letting go. This is a sky crane design. We're kind of coming down, and you see us like lowering the rover down on the bridle, kind of like Mission Impossible, Tom Cruise. And then this is an electrical connection between the descent stage and the rover. This is our landing site, the Jezero Crater Delta Deposit, kind of an oblique view from Mars Reconnaissance Orbiter. And so this is kind of a giant fossil river delta, is the hypothesis, right? That's what it looks like to us. That's what we think it is. And so part of the mission was to go there and confirm that. And because we think it's a fossilized river delta, it's also a great place to look for past life, right? Because, obviously there's probably water here a long time ago. And so we landed in February of 2021. This was our actual landing ellipse, right? Kind of the predicted error zone. And then we landed on the little green dot. And then the novel thing that this mission did was we had onboard hazard detection and avoidance. So we had some cameras that would interrogate the scene while we were still on the back shell. So the rover's kind of tucked away on the inside of this back shell. Takes a couple of pictures, decides if it likes what it sees or not. If it doesn't like what it sees, when it pops out of the back shell in this power descent mode, we would do a divert maneuver and then, pick a better landing site on the right-hand side of this picture, and then we unreel the rover from the descent stage and land, right? So that was kind of this novel first time thing, right? Humans did that obviously with Apollo on the moon. This was the first time that kind of the robot did that on its own. Here's the big Mars 2020. Again, like roughly the same volume and size as Curiosity, but another 100 kilos of drill and other hardware in here, because we had a big sampling system and a sample caching system. Oh, and we brought a helicopter, right? So the cool thing, kind of another plus one, JPL likes to do, right? Our job is to kind of do first of a kind things, right? And so we proposed this little tech demo to do on Mars, the Ingenuity helicopter. And that did amazing things on Mars. You can see it on the ground kind of testing its rotors a little bit after we dropped it off. It was only supposed to go for 5 flights over 30 days, 30 Mars days, and it did 72 flights over almost 1,000 Martian days. So we call those sols, Martian day. Anyway, so that was really cool. And it was kind of demonstrating, can we use a small helicopter to kind of do recon scouting and things like that for maybe a bigger mission, or can it do its own science, right? But it proved we can figure out how to fly on another planet. So that was awesome. A bunch of my friends worked on that, and they were super jazzed. And the main part of this mission is the starting what we call sample return, right? So we're discovering all these things on Mars. But the bottom line is, even though we have very sophisticated, instruments, even if we spend a couple $1 billion putting these rovers and their instruments together, they're still just way worse than the instruments that we have on Earth, right? So to do kind of the really hardcore definitive science, was there life on, in the past on Mars, and a bunch of other stuff like high quality dating, how old is all the stuff that we're looking at? You kind of need to bring all those samples back. And so these are the first 2 cores that Perseverance took on Mars, so kind of marking the official beginning of our Mars sample return campaign. And basically the theory, right, the plan for the Perseverance rover was drill like cache samples, basically grab cores, put them in like effectively a test tube. Like there's a whole nother little robotic manipulation system inside the robot. It takes our cores, sticks them in a test tube, seals them, not quite hermetically, but very tightly. And then leaves them on the ground, or transfer them to another mission to bring back to Earth. That's kind of what's going on. So, so the key results from Perseverance, right, was we confirmed this ancient lake, right, that we confirmed that hypothesis at Jezero Crater. We also saw a bunch of volcanic rocks. So definitely there's like volcanoes just like exploding and throwing rocks all over the planet, including in the Jezero. And then most recently, like this is just a couple of months old now, there's a paper published, there was a big press release. One of the samples that we grabbed looks like it had, multiple indicators consistent with past life on Mars. So again, not 100%, like you kind of got to bring it back to Earth to prove that, but super, super exciting sample that, again, evidence of potential like fossilized life, signatures of fossilized life, things that on Earth we would interpret as potential life, right? And we would take it to a lab to prove that, and we would like to do that. And so we would, again, love to bring that sample back. And we also produced oxygen on Mars. So one of the things, right, unlike Earth, where if you're the early explorers and you sail your ship, your Columbus or Magellan or, the Pilgrims, whatever, you go to a new continent, you can kind of count on the fact that you can probably eat and drink whatever's there. Obviously, when we go to the planets, that doesn't work. So you kind of have to make your own stuff locally. And so when we go on these robotic missions, we often try to demonstrate technology for eventual human stuff. And so we had a tech demo of an oxygen production experiment as well. pick up the pace a little here. So this was the, I guess on the left-hand side is the UAE Hope mission. They had a stamp for their little mission, their little orbiter. And then on the right is the Chinese Tianwen Heavenly Questions lander. So they had a rover that looked a lot like our early Spirit and Opportunity rovers that landed in 2004, but driving off of kind of a legged lander. And then this is, they did a pretty cool PR stunt. They threw off basically a selfie camera on a battery, and then like the rover dropped off the selfie camera and then backed up, and it took a little family portrait. So they were kind of optimizing for PR here. Anyway, so that was cool. And then this is just them kind of driving off their lander. And this is Mars Reconnaissance Orbiter, so the US asset taking a picture of the lander and then the rover that drove off, right? We can kind of see their stuff putzing around on Mars. So bottom line, what have we learned about Mars, right? So we had, I'm going to go through this pretty quickly, right? There's different scales of kind of Mars's history, right? So this is from 0 is time before now, right? So 0 is today, and then 4.5 minus 4,500 is 4.5 billion years ago, right? The beginning of the solar system, basically, to first order. So there used to just be this crater density scale. Most recently, when we got Mars Reconnaissance Orbiter there with much more sophisticated instruments, we also have this kind of mineral scale of what's been going on. There's these very clean lines implied here in these kind of arrows of Mars. Of course, they're much fuzzier than that. There's, the transitions are not like 1 year. Obviously, Mars was kind of warm and wet, and the next year was frozen, right? There's like slow transitions that people just pick some rough dates for those things. I'm not going to go through all this. There's a lot of details here, but the bottom line is, right, we kind of have split Mars's history into 3 periods: the warm and wet period, kind of a volcanic, heavy volcanism and groundwater period where the atmosphere is thinning over time. And now kind of modern Mars, which is this dry, cold, windy, not a whole lot of volcanism, especially today, last few 100 million years. But importantly, right, warm and wet early, right? That's a big deal. So we have like multiple lines of evidence that kind of prove this. And that was a question mark before. Like, was it always dry, cold, and windy, or was something else going on? And so we've proven those kind of left-hand sides. So again, this is kind of what we knew before. Now, right, thanks to this huge amount of public investment and dozens of missions that have gone, kind of that humanity has sent, though, the vast majority of this science knowledge is brought by the US, but we have, substantial contributions from Europeans and others. Right, we have great geologic maps, we have topographic maps, and we have this picture like modern Mars on the right, with poles, north-south pole, and the beginnings, like pretty decent estimates of, yeah, there was probably a global ocean, there were probably lakes filled with water, didn't last very long, but they clearly altered, the surface and left their imprints. And when we go to these places, we find direct chemical evidence that there was definitely water kind of floating around. So, and what does that all mean for Mars, like for life? Like, why did we even go to Mars in the first place, right? Of course, one of the big questions is life, the life in the universe question. Mars being kind of the easiest place to get to in the universe to test that question. And so what do we know? We definitely know, right? Unlike Earth, right, on the left, like Mars is definitely not flaunting its life, not a surprise. But right, we can't rule out this stuff, right? Single cell life might be there, probably underground. If it's there today, it's probably underground, maybe very deep underground. And definitely in the past, it's easy to imagine bacteria making a living on the warm, wet Mars, because Earth, they were all over the place. So that's kind of what we learned, and we really need to bring these samples back to find out. So I'm going to pause there real quick. So any questions on the robotic stuff before I move on to next?
Questions? Got a question here?
Turn the light on. I'll turn the light on first. Go ahead, Dave.
All right. So yeah, I've got a question. I'm Dave. So I'm kind of curious about how you did planning or I assume you were involved in that, but planning horizons, day to day, week to week, mission to mission, balancing science and engineering challenges. Like, as the the Spirit and Opportunity eventually failed, and failed is heartbreakingly is got stuck, right?
Yeah, I mean, much, of course.
Opportunity in particular. So,
Well, Spirit, yeah,
or
Spirit
Spirit,
got
I'm
stuck.
sorry.
Yeah, right.
But in Curiosity's wheels are extremely eroded, so there's engineering challenges there. But
Yeah.
quite apart from that, how did the team pick targets, and over what timescales did you do that sort of thing?
Yeah, that's a great question. And and it was, by the way, I mean, to first order that process, right? So we did have a pretty rigorous process of like both long-term planning, like strategic thinking, right? Because we have this amazing orbital data set, right? We've got pretty decent recon on the whole planet, and especially the landing zone. Like we have good. It's like, imagine you're going on a hike, right? Like, hey, I want to go to Yosemite. I'm going to go on a 3-week backpacking trip. You can go get USGS topo maps, right? All that stuff. We kind of have the equivalent of that, right? So the expedition planning we do well ahead of time, right? And then, of course, the little bit random, like when you go on a hike, you know exactly where the trailhead is, right? Our trailhead is there's a random dice like number generator of like, where in the ellipse do you land? You don't know until you land, right? So then you have to like adjust based on that. And then you adjust based on what you're actually finding boots on the ground versus what you thought you saw from orbit, right? So there are multiple nested cycles, right? And then the tightest cycle is a tactical cycle. That is especially early, again, like I was saying earlier, for the first 3 months, we're on Mars time, 16-hour operation cycle. You've got like 2 shifts of people coming in. And what you basically do is like, you sent commands of the vehicle in the morning, right? Based on your long-term plan, we want to go there, we want to go check out this rock, whatever. You send those commands to Mars in the morning, the vehicle does its thing during the day, and then there's a Mars orbiter communications opportunity in the afternoon. You get that data back in the Mars afternoon time, which could be any time on Earth, depending on where you are in that 37-day cycle because of the 40-minute, 35-minute, right, daytime length shift. And then you have from Mars afternoon until Mars morning, right, like for you to figure out what the heck you want to do the next day. And so that's what you do, right? So that's kind of the high level description. And that was a blast, right? So like the closest I would say I've, being on I'm a space nerd, right? The closest to being on the deck of the Enterprise is working Mars surface operations, right? You've got like 100 engineers and scientists, especially the first 3 months. Everybody's at JPL in the building. You're all hanging out. You're all looking at the data, and you're going through this process of like, what happened yesterday? What do we want to do today? Let's put that plan together. Let's verify the plan, and then let's uplink the plan, rinse and repeat, right? That's a blast. As far as how you make those trades, right? Another great question. So especially for Spirit and Opportunity, right? Those are 100% single string missions on, right? So as in one flight computer, right? Any single thing dies on those missions, like one of the electronics dies, it's lights out, right? Like you're dead. There's no 2 kidneys, 2 lungs, right? There's only 1 brain, 1 lung, 1 kidney, right? Anything in the vehicle gets hurt and it's end of mission. And so Steve Squires, right? I showed you guys that picture of Steve. He kind of had this funny way of talking to us about it. Right. So this is Steve, because you can die at any moment. He's like, look, you have to like plan smartly, but there's a sniper. Like he would literally say this, pretend there's a sniper who's trying to kill you. Right. Like, so plan your day wisely. Like you might die at any moment. Right. And so that was don't be afraid of taking risks because you might die anyway. Right. And so, so we were constantly trying to balance that, like you said, right? And so, and remember the mission, the contract, like the warranty, right, was 3 months of life from these missions. Spirit 3 months, like 1/4 of a year, right? Spirit lasted 6 years, and Opportunity lasted like 13 or 14 years, right? So we way exceeded the warranty, and I think we were willing to take more risks there. And again, places, what happened with Spirit was one of its actuators died, right? So one of the wheel actuators died, and it just got gimpy, and then it got stuck in a sand trap, and it couldn't get out, right? It was kind of the bottom line, even though we tried for like a few months to get it out. And then because the solar panel was at a bad angle, when winter came, it froze to death. So anyway, does that answer the question? Enough detail?
Yeah, pretty much. I wanted to get kind, I followed those missions pretty closely, but
Yeah.
some of the detail of behind the scenes, how you actually did that. And I heard about, working on Mars time and how
Yeah.
how you might have evolved after the first 3 months into, more
Right.
relaxed mission, operations, and did that cadence.
Yeah,
to
and we
play
got
it.
better, right? Like initially, because we weren't efficient, we needed like the full 16 hours, right? And then we eventually got better, automated more of the processes. We kind of brought it down to 8 hours, like one shift, 8 hour operation, right? That let us get to Earth time without giving up too much efficiency, Yeah, and again, I mean, but it really is like every day is like planning a hiking trip at some level, right? Like, of course, you're only planning like a 100-yard hike, right? These are very, very slow vehicles. The top speed of all these rovers so far from the US has been 0.1 mile an hour, right? 4.2 centimeters a second. And so, it's not a very long walk, but you're planning a walk every day and deciding what you're doing with these exquisite instruments and stuff. And anyway, that's a whole nother, there's papers on that. You could look up actually the Working the Martian Night Shift is a paper that describes that process in detail. I was one of the co-authors on that. So if you look up my last name and then, Working the Martian Night Shift, you might get a paper that might maybe answer more questions than I
Okay,
have
thank
time
you.
to get into today. Yeah. Okay.
We have
Any
a
other questions
question.
before I move on to next, like what's going on in the future?
Oh, okay. Well, we have a question from Momo who is asking about the future.
Okay. Yeah. So let me. Yeah. So I didn't. So further out. Let me hit this real quick here. So sample return. This is just kind of shows schematically one of the architectures for sample return. It's been all over the place. So, right, the main thing we're trying to do. So we have, Perseverance, the little red rover on the left here. That's on the surface of Mars. It's collecting samples. It's collecting super like well curated, very well selected high value science samples, and we're going to try to bring 30 of those back in a cache by sticking that cache via different mechanisms. This is one example where we have a fetch rover, but you got to get this cache of samples into the nose cone of a rocket that you have to, so you got to land a rocket on Mars. You got to get the samples in the nose cone of the rocket. You got to chuck, the rocket into orbit, get the cache into orbit. You have to catch the cache with some kind of return vehicle and then bring that all to Earth. So it turns out if that looks complicated and expensive, it is, right? Like our versions of this were anywhere from $6 to $10 billion. That caused obviously a lot of concern with NASA. And even though we were kind of moving out on this, they ended up not having the money to proceed. And so Mars sample return right now is kind of on pause in flux, as the title of the slide says. But that's really the highest priority for this science community is to finish getting these samples home, right? We're still collecting some samples. We probably have like another year of sample collection planned with the Perseverance rover, and then we want to go bring those samples back. That's the robotic priority. And then there's the humans, and that's kind of even messier, right? So this is also in flux. I've got some other slides I could maybe talk to, but kind of where this was in 2023, and it's still mostly correct. Right, there was a 4-phase kind of moon to Mars plan that the US has. This was put in place during I think the first Trump administration. It was actually a pretty solid plan. I think we're trying to execute that, but again, like mostly NASA's having trouble. Like it's an ambitious plan and it's a pay as you go plan, right? So if you don't have the money to do everything as fast as you want, then you just slow it down. So phase 1 is kind of initial human lunar return. And bear with me here, this eventually gets to Mars, right? And I personally am a big fan of going to the moon first. Like we still barely know how to camp on the moon reasonably well. The moon's 3 days away, right? Travel time for astronauts, 3 days of return. You definitely want to like figure out how to deal with a lot of stuff on the moon before you go somewhere like Mars, which with current propulsion technology is more like 6 months away, right? So, and there's a lot of similar characteristics. The lunar dust is really nasty. The Mars dust is also super nasty, slightly different in slightly different ways, but like dust control is a huge deal, right? Trying to learn how to be on your own, and if somebody gets hurt, how to deal with them, right? Like practicing that on the moon, where if you screw it up, you can, like worst case, you send the people back to Earth, is better than going right to Mars and then you're basically dead if something goes wrong. And And so anyway, so that the first few phases here are just getting boots on the ground, then getting more foundational exploration, long-term bases, right? Sustained lunar evolution. Sorry, like so putting permanent base on the moon, kind of like the Antarctic base we have, right? We have McMurdo Station and others around Antarctica. The hope for both the US and I think our competitors, China, Russia, right, talk about having manned lunar bases as well. And then once you kind of have that in the bag, right, you want to start doing the humans to Mars thing. This is kind of another view that shows that exploration that's a little confusing, but just quickly, right? So phase one is maybe through 2030. This is probably maybe now the early 2030s, right? It's kind of slower than we want it to be. And I don't really work this at all, right? So this is all Johnson Space Center, Marshall Space, like the rest of NASA does this. JPL does a little bit, but I have not worked any of this stuff. So getting the human landing system there, those first few, like, so really Artemis 3 is the first human lander, boots on the ground. That's kind of the end of phase one. Phase two then is maybe through the 40s with like you getting more sophisticated capabilities on the moon. And again, all this stuff teaches you about what you need to do on Mars. And these connections here, the little dots, right, are trying to connect like to like technology. Like, learning how to do pressurized lunar rovers is going to help you make a better pressurized Mars rover, and stuff like that. So that's kind of the current thinking, is the moon as a stepping stone as well as a permanent, right, its own strategic value, and then moving on to Mars. Like, personally, if you just camp on the moon and then leave it, the Chinese and the Russians like have permanent bases there. That seems like a bad move strategically for the US. So hopefully, I think it's a good idea to kind of have the permanent base on the moon, but different people have different opinions. And then we move on. Different versions of that same view. So I think the main thing here, right? So people have been planning this for decades now, for the last 10, 15 years, right? The plans have been getting more solid. They change frequently, but the plan, like, as Dwight Eisenhower, right? Dwight D. Eisenhower had this famous quote: "Plans are nothing, planning is everything." So like the plan you can throw away because it's not going to be what you actually do. Going through the process of thinking through all that stuff, right? And realizing what's important and not important makes you a lot smarter. And when you finally have the resources to do it for real, you're going to be just a lot better off, right? Than as if you didn't, if you didn't think about it at all, right? You're going to be starting from scratch. So I think it's still useful progress there. Anyway, that's kind of what I got. So.
Questions?
I have a question.
Yes.
Yeah, no, that was a great talk. Thank you. I have a
Mhm.
question about that wonderful slide you showed where the lander dug a couple of inches into the soil and revealed some ice.
Yep.
Or what is, I guess, everyone supposes is ice. And then after 2 or 3 sols, the ice is gone, so it's sublimated away.
Yep.
I cannot wrap my brain around the idea that that ice, only a few inches below the surface, would have been there for 2 billion years. Is that what people think, or is the ice being replenished from deeper down?
So that's a great point. And by the way, we think there's other white stuff. I think this is CO2 ice, right? That's a little more stable. But the ice in the lower left-hand corner here. So yeah, if you're kind of asking like, what's the modern water cycle on Mars, right? And so I think the bottom line is I don't know the answer. I didn't go back and do the homework on that particular thing. It's a good question. I believe, right? I mean, this is like relatively porous soil. You can imagine a water cycle, right, where water is definitely migrating, right? So in the summer, it's maybe evaporating and moving around, maybe some of that, right? So if the subsurface is a cold sink, so just like old refrigerators before we had our little heating elements in the freezer, right, that would defrost them, you would build up ice in the freezer, right? Every time you open the door, new wet air comes in, that wet air freezes out and it builds up, right, over a month or whatever. You have to you're like breaking chunks of ice off your freezer. So if you imagine the subsurface soil is a cold trap, right? During those periods where we have like net migration, like it's warmer on the surface, you're migrating water molecules around. The ones that happen to like bounce around into the subsurface, you know, they hit this very cold layer and then they're stuck, right? So I think processes like that are credible and probably what's going on. So it might be a mix of actively cycling water, right? That's moving from the very surface to the subsurface that replenishes this stuff, and super ancient water, right? So I'm not showing, I don't think I have it in this like example orbiter data set. There's you know, one of the instruments on Mars Odyssey was a neutron spectrometer, and it made a map of basically hydrogen in the top 1 to 3 meters of Mars, and it showed a lot of you know, and that hydrogen really, for the most part, we think if it's hydrogen, we think it's water. It's bound hydrogen in water. And most of that hydrogen was kind of like in the mid to high latitudes of Mars, right? Places where the maximum surface temperatures aren't sublimating away that ice, right? And so anyway, so I think there's probably both processes, right? Like maybe ancient stuff, if you dig deep enough near the equator. Phoenix happened to land at pretty high latitude. And so it found evidence of what we saw with that neutron spectrometer, you know, probably distributed water underground. I don't know, did that answer the question semi okay?
I think so. I was just
Okay.
wondering, being a bit of a kook myself, if it might have been evidence for the water being of more recent origin, because the other slide you said,
Yeah.
the so-called warm wet period was 2 billion or 3 billion years
Yeah.
ago. And I would
No.
have thought all the water ice would have been gone in that time.
No. So there's lots. I mean, I don't. Let me go back to maybe a global picture. So you can see, like, so there's a north and south pole, right?
Mhm.
So, the you know, I should have brushed up on my Mars geology a little bit more before this talk. Both those poles have a seasonal element, right? So, like I was saying, so this, I forget, one of them is colder than the other. And so one is almost all CO2 ice. The other one is like a mixture of water and CO2 ice. So I think the less cold one, anyway, I'm not going to conjecture here, but there's definitely an active like water cycle on Mars, right? There is still there again. There's buried ice that is maybe hasn't changed in a billion years, like way down underground. But there's definitely an active water cycle that's on an annual basis. And actually, the other thing that happens is Mars, because it doesn't have a moon, right, to kind of give it more like rotational inertia, our Earth Moon system helps, like our, you know, tilt relative to the ecliptic plane, right, in the solar system only varies so much. On Mars, there's evidence that the thing, and I think orbital mechanics and like, you know, other analyses have shown, you would expect every, I forget if it's like few 100,000 years or maybe million years, the whole, like the axis, it switches over onto its side, right? And so like the water cycle gets like totally disrupted. You know, things were like stable water ices today, you know, maybe a million years from now wouldn't be, and then a million years later would be again, right? So there's definitely relatively recent geological motion of water to your, I think maybe
Thanks.
that's kind of corroborating.
Really
what you're saying.
interesting.
Yeah.
Okay, Daniel, another question, again, relating to CO2. If somehow you raise the temperature a few degrees and we're able to sublimate all the CO2 that's in the poles or in the regolith,
Yeah.
what's the current estimate of the total volume of that? I mean, how much
That-
would you raise the atmospheric pressure if you could do that?
That's a great question. Again, I don't know, unfortunately. You know, I mean, just so I'm just going off of like science fiction here, right? So what you're talking about is like terraforming, right? If you want to terraform the planet and make it more hospitable, make it warmer, more hospitable to humans, I have not read any science fiction that implies, and this includes, I think, relatively hard science fiction, that implies just melting or evaporating the poles is enough, right? So I don't think there's enough mass there. But that's a really good question. I mean, if you read the Red Mars, Green Mars, Blue Mars trilogy by Kim Stanley Robinson, right? I think they both try to do that, right? Like access the kind of volatiles at the poles, and they dig like giant holes in the ground to help access volatiles that are underground, right? That we've proven are underground. Um, and usually then you got to like throw more, like you got to go find asteroids in the solar system and like chuck asteroids and comets at the planet. If you want blue Mars, like you got to bring a lot of water from the asteroid belt and the Oort cloud or whatever, like pick your favorite comet source and tow them to Mars and throw them at the planet, right? So it's pretty violent to really get enough stuff to make a real atmosphere.
Any other questions? Yeah, we have one here.
Okay.
You mentioned very early the warm and wet period on Mars.
Yep.
One of the questions is a little hard to imagine. The sun was only about 70% the brightness that it is today at that time. And
Right.
it's way out there beyond Earth's orbit. What would be the source of keeping the planet warm? Lots of CO2, lots of
I mean, I
methane?
think, yeah, A, it's, tons of CO2. B, I think it's also a relative statement. I mean, definitely warmer, but well, actually, I mean, warm enough for liquid water. So let me go to that picture. Where is it? So, yeah, I think, massively more CO2 than our atmosphere, right, is really the key element there.
Okay. We got one more question in the back here. Stand by.
Mm-hmm.
Can you hear me?
I can hear you now. Yep.
Very good. I was involved in testing the Viper mission that got canceled last year.
Oh, cool.
Would have landed on the
Okay.
moon. I'm wondering, are there instruments aboard those rovers that tested VOCs?
So the closest thing, so volatile organic compounds, if we go to the Curiosity Rover, kind of showed a plot here of one of these, like the sample data. So there's the SAM instrument, which is built by Goddard. Paul Mahaffey is the PI. It's the sample analysis at Mars instrument, and it's a mass spectrometer that can either just like suck in Mars atmosphere and analyze the Mars atmosphere, in the mass spec, as well as the tunable laser spectrometer that we had for those methane measurements, and we take these drill samples and we basically, where's the picture? So we take a sample with a drill. There's an inlet at the top rover deck, and then a funnel that goes into the SAM instrument, which is kind of in the rover body up front. And then we heat, the instrument basically heats the sample and measures the gases coming off, right? So you kind of see this plot here, which is how much stuff, right? Different compounds are you seeing versus temperature. And so I don't know if that, I mean, I don't know, but as far as like other volatile organic, you mean VOCs, did that answer your question, or was there a different?
He said that's good.
Okay. Yep.
And one last one, a quick one for you is, so you got European Union, China, India, Russia, United States, all sending stuff there. What are the rules for claiming ownership of the land once they get there? Is there a set of rules written?
That's another great question. So I think you guys might be aware. I think the only thing that really touches on this is the International Outer Space Treaty, right? And that treaty says that no nation can claim kind of anything, moon or beyond the moon, as their own sovereign property. And so this applies not just to Mars, but like moon, asteroids, and I forget, I think the US Congress actually, like it was trying to encourage asteroid mining, and I think Luxembourg, I forget if other countries might have also passed something, but like, again, this hasn't been tested by anybody. I thought there were like, whether it was like law in the US that was encouraging it, I forget the details. or just theories that people want to push, which is, hey, if I go land my thing, especially on an asteroid, right? I think that would be a lot easier test case than a planet. If you're trying to claim some part of a planet, right? That's, maybe strategic, and you're going to get a lot more pushback. But I know there are companies that were considering like landing a spacecraft on an asteroid and saying, hey, we claim the mineral rights to this asteroid. And in the future would send like a mining mission to that asteroid to go mine it. So nobody's done that yet. I think there are people who would love to do that. I know a buddy of mine started a company that Planetary Resources, one of their prospective customers before they folded, was interested in potentially buying a mission just to do that, to just kind of force the legal process to kind of like think through this and figure out how it would deal with it, right? And I think that people are still interested in that, but again, nothing's happened yet. So,
Hey, Daniel?
Yep.
Oh, all right, we got one more.
I
Okay.
get one more. I love having you here, by the way.
Yeah, no problem. Yeah.
I advocated strongly for you to come back.
Okay, cool. Yep. Happy to talk to you.
But one question I have is about, this is going forward,
Mhm.
planetary protection forward and backward.
Oh, right. Yep.
And whether or not you see any significant movement on that now that we've got private entities are itching to go to Mars, and basically a lot of people are itching to go to Mars and bring things back. And I don't know how that will play with previous planetary protection issues. And
Yeah,
how
no,
that will
that's a
change it.
great point. I mean, so I was kind of neck deep in this stuff through 2014 when I was working Curiosity, right? And planetary protection was like a big part of what we were doing. So maybe a little bit of background. So there are like UN rules. I don't know if it's a full-on treaty. I think there might be something close to a treaty that people that countries have signed on to that say, hey, we're not supposed to go contaminate Mars or any other body that might be habitable, right? Like don't take your Earth bacteria and go somewhere that might have water, right? Mars, Europa, right? There's lots of places in the solar system where that might be true because, right, we're trying to protect the science. That's what he's getting at. At a minimum, like we want to know if we find life on Mars or somewhere else, we would like to know that it's an independent, whether it's a second Genesis, right? Or, it's a we're finding unique life and not like technician Ted's skin cells, right? Like that the last mission dropped off on the planet, right? So that's kind of the job of the forward protection. And yeah, I think there's so US, we've always taken that very seriously, and it has made life hard for us engineers when we engineer this stuff and how clean we have to get everything and all that stuff when we land. I don't think we have a lot of insight into how clean the Chinese lander was, for example, and how seriously they're taking that, right? And I think especially once you get like the wet protein bags, right? Like water bags that are humans on the planet, right? It feels like that's going to be a lost cause, right? Like at least the forward contamination is probably quickly going to be a lost cause. At least that's my like layman's, kind of engineering take. I don't know how you would possibly in any credible way without spending $1 trillion, like, having an airlock that like fried everything, like it would be crazy expensive, like to try to meet planetary protection requirements once you have humans there. And so anyway, before then, that's another reason why we're trying to do sample return now, right? Like those samples that we're collecting with Perseverance are pristine samples, relatively clean. There's only been a little bit of human trash on the planet, right? Most of that human trash has been, we've taken great pains to clean it. And so hopefully those are pretty, high confidence that that's like real life detection of a new thing and won't be spoofed. But all bets are off once the humans start walking around. I don't know. Does that help a little bit?
Yeah, sure. Okay. One last question, Daniel.
Okay.
I'm Richard Drum of the 365 Days of Astronomy podcast.
Cool.
You mentioned that Mars, because it doesn't have our moon or something significant like our moon, stabilizing it, that it'll flip its poles north-south. Is that the Zanabakov effect?
It's sideways. I think it's sideways actually a little more. And I don't know.
The
So-
Zanabakov effect is named after Vladimir Zanabakov, who had a T-handle wrench on Mir, and he would spin it and notice that it would simply flip ends, turn 180 degrees periodically. And it's been done on the ISS too. It's kind of a cool little parlor trick.
Yeah, that's an interesting, I mean, so there's definitely like a thing, like a known thing, mechanical engineering, which I can talk to, right? Like moments of inertia, you have a spinning body. If you're not spinning about your primary, like your axis with the highest moment of inertia, right? You're gonna eventually lose energy and you will eventually spin about the highest moment of inertia axis, right? So, but I think the planets have been around long enough. I don't think that's what's going on, right? Um, so I think it's some other like gravity, sun, moon, Jupiter, like other weird stuff, right? That like influence these things, I think somewhat. But again, I don't know. So I don't think it was the same thing going on with the wrench there, but I could be wrong.
Hey, Daniel, this was absolutely fantastic. This was great. I'm going to contact you.
Okay, cool. Yeah, my pleasure, guys. It's always, and you guys are so smart. I always forget I need to do like more homework before I have these talks because you guys are definitely like average than the average audience, smarter than the average audience on this stuff. So it's, yeah.
Well, I'm gonna contact you tomorrow, see if I can get you about another 18 to 24 months out again.